Hello everyone. In this talk, I'm going to attempt to show how the Rust type system can be leveraged to write more elegant DSP code. We're going to start with a brief overview of the relevant parts of the language, and then we'll see how what we've learned can be applied to construct types and traits that will be the sort of foundation of a DSP library we'll be developing over the course of the talk. As we progress, we'll then see how to apply sort of increasingly abstract and advanced features of the Rust type system to make our DSP elements more composable and modular. But first, sort of as a point of clarification, what exactly do I mean by elegant? So for the purposes of this talk, I'm going to define it with the following list. First, we have expressivity. So we want code written with our library to be concise and readable. Second, we have flexibility, so we want this code to be usable in a variety of contexts. And then finally, we have composability, so we want the elements initialized with our library to be easily combined into audio processing graphs. And we want to achieve a balance between these without there being much of a cost in terms of safety or performance. So my expectation is that you're coming into this talk knowing something about programming in DSP, but not that much about Rust specifically. So I hope by the middle of this talk, you'll have enough understanding of the Rust type system in order to decipher some of the cryptic-looking abstract types that we'll be developing in the process of creating the backend for a DSP library. And when this process is done, we'll have created most of the fundamental data structures needed for DSP programming, and we'll have a sort of simple interface to our library with elements that can be composed using a functional syntax. Our kind of main goal for this library is that it says, it can be used sort of like a domain-specific language like Faust, so it has a very convenient syntax. But it's implemented just using more advanced features of the Rust type system rather than, a domain-specific compiler. So to make sure this talk is broadly accessible to people who aren't Rust experts already, I'm going to introduce the new aspects of the Rust type system as they become relevant to the feature of the library we're developing. But we're going to move quickly, so anyone watching this talk online might want to read some introductory Rust resources first. And we're going to start by implementing the sort of simple, naive versions of various library features like buffers and processors, and then we're going to gradually iterate on them to take advantage of more advanced features of the Rust type system. Okay, so first some basics. Like many languages, Rust supports composing types into structs, as well as implementing methods on those structs. Just as an example, we can make a first pass at creating one for an audio buffer. As you can see, this buffer is essentially a wrapper around a single member, which is a vector of 32-bit floats. And we can implement various methods on this struct. So as you can see, our first method simply returns a new instance of self with an empty vector. Since it doesn't take a self type as an argument, it should be called using the double colon syntax instead of the dot syntax. And it won't have access to any member variables. It's a sort of standard convention for the new function to create a new instance of some type. Our other methods both take a reference to self. You can see that the first one just returns the length of the buffer, and that the second one zeroes the contents of data. Importantly, you may also notice that the second one takes a mutable reference to self. In Rust, variables are immutable by default, so in order to modify the contents of data, we need to use the mute keyword when getting a reference to it, so that the compiler will let us mutate it. Okay, so also, like in other languages, Rust has support for generics, which can be used in both structs and functions. We'll use a generic to generalize our audio buffer type into a buffer type that can be applied more broadly. So as you can see here, our buffer type is now generic over any set of items, which we've given the generic argument t. Notice that in this example, since t isn't guaranteed to be a number or any other type, we can't implement the zero method on it. However, we can implement this method for a specific value of the generic, as you can see here. In this implementation, it specifically applies to a buffer containing 32-bit float values. If we want, we can also alias our buffer of some specific type to some other type name. So we might alias a buffer of 32-bit floats to an audio buffer so that it can be used like in the previous example, and we could, if we wanted, alias a buffer of type note to a note buffer. So as you can see, now our audio buffer can be used just like in the previous example, but it's now backed by the more flexible buffer type. So now with some of those basics out of the way, we're going to take a brief tour to introduce traits, and we'll return to our buffer struct once we covered traits and trait bounds. So superficially, you can think of traits as Rust version of a class or interface, and they can be used to define a set of methods associated with that trait. Now, for our library, we'll start with the example of an audio processor. And here's a sort of naive implementation of our trait. Now, as you can see, our processor trait has unimplemented prepare and process methods, and we can then implement this trait on any type we want. We use a simple distortion as an example. So as you can see here, we declared a distortion with a new and set gain functions, and then we've implemented our audio processor trait on it. Okay, so the next feature we're going to introduce is called the associated type, which we'll use to generalize our audio processor into a processor. Associated types are ones that are named in the trait definition, but are left unspecified until the trait is actually implemented. So here's a quick example. As you can see, we've generalized our audio processor trait into a processor trait, which has two defined associated types, input and output. You can see this version captures much better the essence of what a processor is, right? It's a device that transforms some input into some output. And then we can now implement our new trait on the distortion type as seen below. All right. So notice that we've assigned float32 to be the input and output types of this processor. And since we've generalized this trait with associated types, we can also implement it on our distortion multiple times if the associated types are different. So for example, we might also want to implement it for the 64-bit float. Okay, but wait, it's starting to look like we have some unnecessary code duplication. And we're going to eliminate it by writing a single processor implementation that's generic over any kind of float type. Now, for this more abstract example to work, I'm going to need to introduce two things. First, I'm going to introduce the float crate, which has a trait called float that is implemented on various floating point numbers, including 32-bit floats and 64-bit floats. And then secondly, I'm going to introduce a feature known as trait bounds, which is used to add constraints to generic parameters. And we'll see how this works with a simple example. So as you can see here, in each of our implementations, we've defined a generic parameter f, which is used to constrain some type to be one that implements the float trait. We've assigned f to be the input and the output of our processor. And since the float types are guaranteed to support adding and multiplication, we can perform the necessary arithmetic in our process method. I'll repeat this just for emphasis. If in our processor implementation, f wasn't constrained to be a float, then the compiler wouldn't let us multiply the input with the gain value, since the generic parameter wouldn't be guaranteed to be a type that can be multiplied. So the trait bounds are an essential part of making this more abstract implementation work. So now that we understand something about how trait bounds work, we can go back and apply it to our buffer type to implement a few useful methods that will apply anytime the buffer contains a float. So notice in this new implementation, there's a generic parameter f that's constrained to be a float type. And then we've implemented two methods. You can see in the first method, it'll simply fill the buffer with a equilibrium value associated with that float type. This is a constant value that for a 32-bit float or 64-bit float would just be 0.0. We also have an add from method, which will add every value from a source buffer to the current buffer. Since float values are guaranteed to support copying, addition, and assignment, we can use the relevant operators when implementing this method. So as you can see here, this these new method implementations will be generic over any kind of float. Okay, so at this point we've introduced most of the basic language features we're going to need when developing our library. So we're going to take a moment to step back and think more about what we want this library to accomplish. So as mentioned earlier, we want users of our library to be able to write DSP code that's expressive, flexible, and composable while being safe and performant. And here's some of the specific features we're going to look at together that will help us accomplish this goal. So first, we want the sort of DSP elements in our library to be generic over multiple sample types. We've already seen how to make processors that are generic over float types, but we want to extend this to multiple sample types, which kind of by definition in this library may have multiple channels. And we also want to make our library generic over multiple buffer types. We don't just want to restrict the user to using our included buffer type. Real audio code may need to interact with other libraries and languages. So all our buffer processing functions should support, both our own buffer type, built-in Rust types like slices and arrays, and even raw pointers that you might get from a C or C++ library. We want to have useful methods auto-implemented for most of our types. And then we also want a simple way to initialize and compose our elements into processing graphs. And, the Faust programming language will provide some, good inspiration for this. Note that our goals of expressivity, flexibility, and composability are for the users of our library. Implementing the library itself is going to require some fairly abstract uses of the Rust type system. So prepare yourself to look at some gnarly code, and knowing at the end, our library will be friendly and flexible to use, though a user inspects the contents of Z library at their own peril. Okay, so we previously saw how to write code that's generic over multiple float types using the float trait. And so our next task is going to be to make our library generic over multiple sample types as well, which we'll do by creating a sample trait. By sample here, I mean a single snapshot of some continuous time signal that may have multiple channels. So, in our library, a sample may be mono, stereo, or even in a spatial format. By making our code generic over all these sample types, we'll be able to implement our DSP elements one time over all these different channel formats. So our first step is to create a few of these sample types. Our basic single channel types will just be float values, as we previously saw. But we can also create one to represent a stereo sample as an example. So as you can see here, our stereo sample contains a float representing the left and right channels, which we can, if we want, we can also implement, helper methods like pan on our sample. Okay. Now the next step to making our library generic over all the different sample types is to create the sample trait, similar to the float trait that we were using earlier. Now, as you can see here, we've declared a sample trait which has an associated float type, which is required to implement the float trait. Our trait also has two associated constant values, channels and equilibrium, which define the number of channels associated with that sample, and then also kind of what the zero equilibrium value of it is. And then it also has a bunch of functions that may be used on that sample type. I have some here. In a production library, you'd probably want even more. You may have also noticed at the top that the sample trait is further constrained so that it must implement some other traits like copy, clone, and add traits. This add trait constraint, you can see here, takes a self value and then also outputs a self value. So it'll take a type of that sample and output a type of that sample. If you're implementing a library like this for yourself, you'll want to add a bunch of other constraints for operations like subtraction, multiplication, division, and so on. I'm just covering just enough to get the core ideas across here. Okay. Now, the next step is going to be to implement this sample trait for every sample type that we want to support. I'm not going to do that for all of them here, but the process would look something like this, right? So first we implement the sample type on a 32-bit float. And then on our stereotype, which is generic over different kinds of floats, you'd want to fill in all the relevant methods for each implementation, and you could continue expanding this list to include support for spatial audio samples and any other kind of sample you like. So once this is all implemented, it can be, kind of used simply as shown below. You can see here we have a test function that's generic over all sample types, and it makes use of some of the methods defined in our sample type, as well as operators like multiply. This test method doesn't do anything particularly interesting. It's just meant to showcase how we can now use, the different operations we defined on our abstract sample type as opposed to a concrete type. Okay. So now that we've got some of the basic building blocks to make our library generic over different sample types, we're also going to make our library generic over different buffer types. And to do this, we're similarly going to implement a block trait, which will represent some non-owned frame of samples or other data. Here's a sort of first implementation. Now, since most generically a block is just a list of items, we'll have a corresponding item associated type. And for our block to be useful, we will want to be able to access these items somehow. And so we'll have methods to retrieve them as a list or slice of items. This is just the kind of Rust built-in array type or reference to an array type. We can implement other useful default methods on our block using type constraints. So just as an example, we'll say we want to implement a RMS method for whenever the block contains samples. So first consider the signature of this method. What we want to do is constrain the implementation of our function so that it's only available when the block item implements sample. And that will translate into the signature you see here. You can see that we have this where clause that constrains self item so that it must implement sample. And then the actual implementation of our RMS method is below. Now, as you can see, this method is perhaps a little more verbose than one you might have seen implemented on concrete types. The advantage of this abstract implementation is that the method will now be available in our library for any combination of types that implement float, sample, and block, right? And, because there's many different kinds of floats, many different kinds of samples and many different kinds of blocks, this is, you get a sort of combinatorial explosion of the of the number of situations that will be supported by these are the abstract implementation of the method we have here. Okay. Now, just as an example of a method that will mutate the block, we can also add a copy from method that will copy values from some source block to our current one. Now we have our implementation here. The signature from the copy from method might look a little complicated, but if we walk through it, you'll see that it's actually fairly simple. The method first declares some generic parameter b, and as arguments, it takes a mutable reference to self and an immutable reference to some source block. The first constraint you can see after the where clause ensures that the item is copyable, so that we can actually copy it from one block to the other. And then the second constraint ensures that the items in the source and destination block are of the same type. Now, importantly, notice that this method does not require that the block types themselves are the same, only that the contents of the blocks are of the same type. So this can be, this abstract method can be used to copy between two completely different types of blocks, as long as they both implement the block trait and contain the same element types. Okay. So now our last step before being able to use these methods is to implement our block trait on all the types we want to support it, like our buffer type, Rust built-in arrays, raw pointers, so on and so forth. So just an example, we'll first implement it on the buffer type that we saw before. And then we also have an example implementing it on the Rust built-in array type. And then finally, in this example, we've implemented our trait on a tuple containing a sort of raw pointer to some samples and a size. Okay, so now that we've got a couple of methods implemented on our trait, we can get the sense of what the payoff is for these more abstract implementations when using the library. So we'll showcase this using the following example. So as you can see in this test method, it takes three entirely different buffer types as arguments. First, the raw pointer type, then the kind of Rust built-in array slice type, and then the buffer type we were working on before. And you can see that though this method takes three entirely different buffer types, we can use the once implemented copy from and add from methods when transferring data between these buffers. So this interface greatly simplifies our our interaction with these multiple buffer types. Without this abstract implementation, we would need to implement custom copy from or add from methods for each type. Now this method was implemented on 32-bit float specifically, but if we wanted to, we could make this method abstract over any kind of float or sample type. Here's just a quick example of making our method abstract over all sample types. Now, with this method, we could use it on any sample type we wanted. Whether this be, we could pass it, a buffer full of basic floats. It could be stereo audio data. It could be spatial audio data. It would all work the same because this, sort of abstract implementation of our copy from and add from methods, supports, is generic over all these combinations of types. Okay. Now, the next thing you'd probably want to do if developing this library for yourself is to implement a sort of laundry list of useful functions on our block and float traits. This could include methods for, convolving blocks of audio data, equilibrating a block, applying functions across a block. It could be, functions that are specific to buffers of notes as opposed to buffers of audio, so on and so forth. These implementations, if you implement them once on the trait, will become automatically supported on all the different block types, and will also be supported between all the different combination of block types. So again, you'll get a sort of combinatorial explosion of the supported use cases of your abstract methods. Here's just a few examples of some ones you might want to implement. So, first we have an apply method that will apply some function to each sample in the block. We have a gain function that will apply some gain to each sample in the block, where the item is constrained to be a sample. We have a method that will fill the buffer with some value, and we have a method that will equilibrate the block, again, if the item in the block is a sample. So though these implementations are a bit abstract, they can be used easily as shown below, right? So you can see here in my test 1 and test 2 functions, we can easily apply these methods to 2 different buffer types. So you can see it can apply them in the same way to both the buffer type that we used earlier or created earlier, and to a buffer we might get from a C library that's just a raw pointer to some data and a size. Okay, so I think that covers how to implement abstract methods over different combinations of float, sample, and buffer types. Regardless of if you thought the abstract code was a little complicated or hard to read, I hope the final examples make it clear how simple and flexible the end result is to use as a user of the library. Remember, these functions can be used on, with any permutation of float types, channel formats, and buffer types. Okay. So next, we're going to take a closer look at DSP processors and how they can be represented in a way that's abstract and composable. Just a reminder from earlier, we represented our processors using the following trait, which consumes an input and yields an output. And while we're at it, we'll also create a generator trait, which only produces an output. Now, what we're going to do is we're going to try and use the trait system to allow types that implement these traits to be composed into audiographs with operators, similar to what you might see in the fast programming language. So here's a sort of preview where we're going. You can see I'm initializing our DSP elements using simple function calls with parameters, and then composing them with operators, like the right shift operator. Now we'll start this process by considering the node composition. Okay. So while there's many ways to compose our nodes, for the moment we're going to be focusing on implementing what I'll call chain composition, which will just feed the first element into the second element, and this will be accomplished using initialized using the right shift operator. To support this, we're going to be implementing the shift right trait, which contains the method that's called by the Rust compiler anytime the shift right operator is used. You can see the trait definition here, which basically there's a left-hand side and a right-hand side, and then it produces some output. So we need to implement the shift right trait on a single type, but we want to be able to compose a variety of different processors and generators. So, in order for this to work, we're going to need to create a single node kind of wrapper type that can be composed with all our operators. And this node wrapper type should be able to play back any processor or generator that it contains. So here's a simple declaration of our node type. You can see that it has a single generic parameter p, which is used as the type of its only member. And to sort of drive the conceptual point home, you can see I created the following diagram, which shows how each generator and processor would be wrapped in a node type, and how each of these nodes would be composed with operators. Again, this is a diagram, not meant to be Rust syntax. So now consider each of the operators. How can we use the shift right trait to get the desired chaining functionality? We're going to use kind of the solution I came up with is that we're going to use the trait to generate a struct chain, which will wrap the elements on either side of the operators and call the elements in the appropriate order. So a struct chain will contain two elements that are fed from one into the other, kind of as shown below. And these chains can be composed recursively. So the idea is that compile time, using an operator like you see in the first diagram, will generate a data structure like you can see in the second diagram, where each pair of nodes is wrapped in a chain type. And this diagram represents the data structure that we want our operators to produce at compile time. Okay. So since we've already implemented the node struct, the next thing we need to do is implement the chain struct. Be forewarned, this is probably the most gnarly type we're going to see today, so if you don't quite wrap your head around it, don't worry. Actually, using the library doesn't require understanding it, but I'm hoping to walk through it. So the heavy use of generics in this example might look intimidating, but if you go through it line by line, it's actually fairly simple. So first you can take a look at our implementation of processor for chain. You can see that there are the generic parameters P1 and P2 to represent the two different processors in our chain. And these are used as the first and second argument, or first and second member in our chain type. Then you can see we have these three generic parameters in, between, and out. And these are meant to represent the sort of input to the processor, the type in between the chain processors, and the output type. And most importantly, you can see after this where clause, where we constrain the P1 and P2 both to be processors. The most important thing here is you can see the output of P1 is given the same generic parameter as the input to P2. All right, so this basically ensures, it requires a compile time that the output of the first element in our chain is the same as the input to the second element in our chain. Okay. So, and then you can see that our method implementations are fairly simple, kind of what you'd expect. The prepare method, just calls prepare on both elements of the chain. And then the process method will call process on the first element in the chain, and then feed that output into a call to process on the second element in the chain. Okay. So now that we have both our node and chain types, we can implement the code that will generate the sort of diagram that we saw before from our operators. And we'll do this by implementing the shift right trait for creating chains. So as you can see here with our implementation, it'll have some self type, which is a node on the left, and then on the right hand side there will be another node. And the result of this trait being called by the compiler will be a node that wraps a chain that wraps both our elements on the left and right. So when the right shift operator is applied, it will transform the nodes on either side into a single node containing a chain of the left and right hand nodes. Okay, so now we've implemented the code we need to compose our audio nodes. And then the next step is going to be to create the functions that will produce these nodes from our processors and generators. So our node initialization code. Okay, so how can we initialize these nodes? We're going to start just using an example implementation of struct gain, which implements processor generically over all samples. The details of how our gain struct is implemented aren't that important. What is important is that we can create a const function that just creates an audio node from this struct as shown below. All right, so you can see here we take a decibel value as input, and then we return a node containing the gain processor that can be used to apply a gain to some input to produce some output. All right, so it looks like we have everything we need to start composing nodes. You can assume I repeated this process for some other nodes other than just gain, but given that, this is how we would then use the library. So you can see here on the first line, we first will call our noise function, which will create a node that wraps our noise struct. And then you can see in the second line, we call our gain function, which will create a node that wraps our gain struct. And then finally, on the third line, you can see I can compose these using the right shift operator, which will produce a node that wraps a chain that wraps both of the initial, the first nodes that we created. Okay. Now, the last thing we need to do to make this, this composition actually useful is we want to be able to call the generator and processor methods on our completed graph. And so to do this, we just need to implement the generator and processor traits on the node struct, as you can see here. So as you can see in each of these implementations, each trait is only implemented if the members of the node implement the appropriate trait, right? So the processor trait will only be available on the node if the containing member is also a processor, as you can see from the where clause, where we constrain the contained the P generic value to be a processor. Okay, and then now that we've done this, we can freely compose and use our nodes as shown below. So you can see kind of on our first line here, we have a simple graph initialization using the right shift operator and our noise. We have sample generation, so we can now call the generate function on our graph. And if you remember before, we had implemented a whole list of functions on our generators by default, and so we can call any of those too. In this case, we call our generate block function to generate a block. Now, since this graph starts with a generator and ends with processors, it will be the generator methods that are available for the whole chain. But importantly, if I switch the first element to a processor, then you'll see that the generator methods are no longer available for the chain, and instead I can call the processor methods. This is the sort of magic of type inference in the Rust compiler. Right, so in this second example, I've switched the noise for a distortion that just processes input as opposed to generating it. And then now the available method to me is to process some input as opposed to generate it from scratch. And again, I can use the relevant block processing methods also to process some input block into some output block. Now, what I showed was specific to the right shift operator, but this general strategy can be expanded to include operators beyond just right shift. You may want to be able to split and combine streams of data using the and operator or whatever other operators you want to implement traits for. Doing that is left as an exercise for the listener. So we covered a lot in this talk, and we got fairly deep into the weeds with some code, so I hope it was all intelligible. I also hope I've made the flexibility benefits of the abstract method implementation sufficiently clear. The same graph initialization code we just saw can be used with any combination of 32-bit and 64-bit floats. It can be used to generate mono, stereo, spatial channel formats, so on and so forth. The same code can also be used to generate buffers and process buffers for all the different buffer formats we saw, whether that be the built-in Rust one, the buffer type we created, or raw buffers we get from a C library. And any of the laundry list of default functions we've implemented for processors and generators will be automatically available for any node graph that we construct with these operators. The techniques I covered were derived from a DSP library I've been working on for a while. It's not quite ready for public release now, but I hope to put it on GitHub before this talk is posted online. And it should have more features than just the ones I've covered today. And overall, I hope this talk gives people some ideas of how the Rust type system can be used in their own projects. and I look forward to any questions the audience might have.